All right, class, so let's continue. Sorry. All right, there you go, better. With this section 4.5 and find this time the minimum of this function right here under this condition. So one more time, that means this f of xy equals to ln of x squared plus y squared is our objective function. And then this condition here will make it into a constraint function by setting or moving all the terms to one side of the equal, right? So remember, whatever would equal to 0, that's your g function right here. Okay, and out of the two, we create the Lagrangian of x, y, and lambda by doing what? Taking the function f of x and minusing lambda times the function g of x. Okay. And then remember, your critical point that you get from this problem is going to be the solution or the answer to this. Okay. All right, so let's see. What is Lx? What is Ly? And what is L lambda? Okay. So the derivative with respect to x, I'm going through this first term. It has an x in it. However, there's a natural log on top of it. So the derivative of an ln is 1 over whatever's inside that log times, move on to the parentheses. Inside the parentheses, the derivative of x squared is 2x minus, there's another x in here, so the derivative of negative 2x lambda is negative 2 lambda. Okay. The same thing, Ly will be 1 over the x squared plus y squared, then this time times 2y, minus only what? 1 lambda. So the derivative of lambda y is lambda. Okay. So as I said, you'll set these equal to 0 and solve each of these equations for lambda. That's how we move on. Of course, there's a third equation, which is basically your condition. So the derivative with respect to lambda, there's no lambda in here. So the derivative with respect to lambda is the negative 2x plus y minus 25, and that equals to 0. So that means the 2x plus y minus 25 is 0, right? So that's your condition right here. Now again, remember, the best method to solve this is to solve both these equations for lambda and set them equal to each other. So this is what I would get. Combining this fraction, I will get a 2x over x squared plus y squared is equal to 2 lambda. Yes. So I move the 2 lambda over to this side of the equal. And then I combine that fraction. Now, sure enough, I can divide both sides by 2. Oops, not y, but lambda. I can divide both sides by 2 to get to lambda. So lambda is equal to x over x squared plus y squared. Done. Now, out of this equation, pretty much the same, except for what? I have a 2y over x squared plus y squared, and then equals to lambda, so just a lambda. So there's nothing to solve for lambda anymore. There's lambda by itself. So combining these two equations, what do I get? That, here, let me write it down here. I get the lambda, which is x over x squared plus y squared, is equal to this lambda, which is 2y over x squared plus y squared. So even though it looked a bit scary, you can multiply both sides by x squared plus y squared, and what's going to happen, since these two denominators are the same, you'll simply get the x must equal to 2y. It's just as simple as that, right? So these variables with respect, or these functions were completely similar with respect to x and y. The only difference is that I had 2 x's here and versus 1 y over here, right? So solving this, that means really that the x must be twice as much as y. Okay, right, so this is what we got combined from the first two equations. So we combine this again with what? This third equation that we had into a system. So I have that x is equal to 2y. That's what we found from the first two equations. And then the third equation is basically my condition that says that 2x plus y minus 25 is equal to 0. So same as the problem up above, I think the best way to solve this problem is by substitution, right? Since you have this x already by itself. So I'll write it under here. We'll get that instead of x, I'll write 2y. That's what x equals to. Plus y is 25. I move the 25 over. So sure enough, I'm getting that 5y is equal to 25, which means y is 5. Plug it back in to get the x. X is 2 times y. So x must be 10. There you go. So your critical point for this problem is 10, 5. So it said, trust that you will find whatever we are asking you for. So the minimum is found at the point of coordinates 10, 5. So x must be 10 and y must be 5. And that minimum value is, again, my function was natural log of x squared plus y squared, so it's ln of whatever 125 might be. It's something that comes out of your calculator where you just leave it like that. That's your minimum value, yes, for this function. And that's when it occurs. All right, there's that. Okay, so let's move on. Okay. This is the problem that I initially had in mind, but just as I was reading over it, it made me think of the problem that you guys had to do for your exam. And I'm thinking maybe we can solve your exam problem. And there I'm bringing it up. Maybe we can solve your exam problem using this new method. Thank you. So there it is. It's the same pretty much. We have a rectangular garden with an area of 144, and I'm just going to make it 800 square feet. Okay. The cost of the fencing material is $5 a foot, but let's change it to what? $5 a foot for one side. Let's say for the width, it doesn't really matter. Okay, $5 is for the width, and let's make it $10 a foot for the length, just like your test problem. Okay, minimize the cost of fencing the enclosure. So what do I know? I want to minimize, here, let's draw this enclosure. I'm going to draw it up above to save some room. This is my enclosure. It's a rectangular enclosure. So you have a width and you have a length, okay? And we know the width goes at $5 a foot. And we know the length goes at $10 a foot, okay? And we know the area of this whole thing is given to be 800 square feet. Okay. All right, so what do we want to do? We want to minimize the cost of this enclosure. And what does it cost me to enclose this rectangular garden area? Well, this side is $5 a foot. This side is $10 a foot. Don't forget, you have not just 2 sides in this rectangle, but you have 4 of them, right? So some of you messed that part up on the test. Okay, it's not just a 5x and a 10y, it's 2 of these 5x's and 2 of these 10y's. So the cost function is 10x plus 20y. Great. What are we give? So this is our objective function. Yes, we want to minimize it. What do we know? We know under the conditions, so our constraint is the area of it has to equal to 800, right? So that's our condition. So our constraint function will be made into a g function by throwing the 800 over to have it equal to 0. Okay? Okay. So, now out of these two functions, the cost and condition function, we're going to make, there you go, we're going to make a new function, which is what? Ooh, I know what I'm going to say also. The Lagrangian. So x, y, and lambda. Okay. So that's going to be our condition, our objective function, which is 10x plus 20y, minus lambda times our condition function, which is xy minus 800. Okay. So let's find the three partial derivatives. Lx is going to equal to 10. The derivative of this lambda xy with respect to x is lambda y. Ly is 20 minus the derivative of this term with respect to y is lambda x. And of course, lambda, L lambda is your condition. Yes. So the derivative with respect to lambda is negative that. So set them all equal to 0 and solve the top two for lambda. So 10 equals to lambda y, which means lambda is 10 divided by y. 20 is equal to lambda x, which means lambda is equal to 20 divided by x. So as I said, from these two, we're going to set them equal to each other and make a new equation out of that. So we can cross multiply and get that 10x is equal to 20y. Even better, x is equal to 2 times y. Okay. All right. So combine this equation now here. I think I'm just going to take this to a separate page. Combine the two equations. So I have x is equal to 2y and what? xy minus 800 is equal to 0. Okay. So what do I do again? Maybe substitution, yes? So plug in this 2y here in place of x. So what I'm going to get is this. I'm going to write it underneath. So jump over this. We'll solve this problem on a separate piece of paper. So I have, instead of x, I write 2y times y minus 800 is equal to 0. So 2y squared minus 800 is equal to 0. So 2y squared is 800. So y squared is 400. Take the square root on both sides and just keep the positive value of it, right? Because it's a side in a rectangle, so it cannot be negative. Okay, so combine, what else do I know? I know that x was equal to 2y. So x must equal to 40, yes? So there you have it. It says the area of a certain rectangular enclosure is to have an area of 800 square feet. Minimize the cost of fencing the enclosure. So the minimum cost will be at 40, 20. And remember, what was the cost function? The cost function right here was 10x plus 20y. So 10 times 40 plus 20 times y. So that's 400 plus 400, which is $800. Okay, so that's the minimum cost for it. Now, we haven't done anything about this lambda, and I'm kind of getting annoyed that we haven't talked about it yet. It's in your textbook. It's in your textbook, but I haven't mentioned the lambda yet. So I'm going to take this aside. And I didn't really want to talk about lambda unless we had a problem that really had some meaning to it. So what's the meaning of lambda? The meaning of lambda is that lambda is going to equal to the it's the amount of extra objective function units with respect to any extra, I should say, constrained function units. Okay, so what does that mean? That simply means that what? For every, what are our objective function units? The objective function is the cost, right? Minimizing the cost of materials. So it's dollars, yes. Extra constrained function units, the constrained function is the condition that was given. The condition that was given is that you have 800 square feet. So what we are saying is simply that if you put one extra square foot, into this enclosure, so you make it what? A little bit larger, yes, so a little bit larger enclosure will definitely mean a little bit more what? A little bit more fencing, yes. You will get this many extra dollars, right, in your cost. So we haven't found lambda yet, so let's go back to find lambda. Where is your lambda? Here it is. Lambda is equal to 10 divided by y, or 20 divided by x. So for us, I will write it up here. Our lambda is 10 divided by y, which y is 20, yes? Or 20 divided by 40 is the same thing. So it's a half or 0.5. Okay, so what does that simply mean? It simply means that if you're going to put one extra square foot of area in this enclosure, the cost of the fencing will go up by 50 cents. Okay, so for every extra square foot of added in here to your enclosure, the cost of this fencing will go up by 50 cents. You put 2 more square feet in here, yes, you stretch it up to fit 2 more square feet, it's going to cost you another $1 of fencing, right? And so on and so on. So that's what it means. For every 2 extra square feet of area, you get $1 more added onto your cost. So that's pretty cool to know. Well, what if I want to make it a little larger? What if I want to make it 900 square feet? I don't want to solve the whole problem again. 900 square feet means $50, right? Extra, right? So there you go. The half. All right. So let's look at this problem, which is a Cobb-Douglas function. All right. So here it is. I got all of it. Here's your Cobb-Douglas function. It says, we are operating under this budget constraint, which is huge. In other words, it tells you what? That it's going to cost you, that you can only spend $8,000. Yes, it's a budget constraint. You only have $8,000 to spend on what? 50 labor units, right? So 50 hours, right, of labor, whatever you're paying your employees for, but you can only pay them for 50 hours. And $100 a capital unit, whatever the capital unit is like amount spent for machineries, right, buildings, materials, and so on and so on. So you can buy 50 of that and 100 of that for $8,000. That's how much you get to spend. Okay, so this is your objective function, and this is your constraint function. It even says right here. Okay, so out of these two functions, we're going to create the Lagrangian. And again, I know this might be a little bit confusing because you have an L of L, but again, that's labor units, that's your Lagrangian, right? Here, I can make it a little bit different L if you want. So how do we make that? It's 200 L to the 3/4 K to the 1/4 minus lambda times 50L plus 100K minus 8,000. So remember, your G function right here is whatever you get once you move all the terms to one side of the equal. All right, there you go. Yes, okay. So this is your Lagrangian. All I want to do is find the three partial derivatives, set them equal to 0, and that will do whatever we want to do, which is maximize the production function. Okay, all right, so let's get to work. Let's just find the derivatives. So what's the derivative with respect to L? The derivative with respect to L, first of all, I'll keep the 200. The derivative of L to the 3/4, I'll bring the 3/4 up front, times L to the negative 1/4, times K to the 1/4, minus, the other term with L is the negative 50 lambda L, so minus 50 lambda. Okay. The derivative with respect to K, keep the 200 coefficient, times L to the 3/4 x just as a coefficient, it doesn't have a K in it, times the derivative of the K part is 1/4, K to the 1 less than 1/4 is negative 3/4, minus the derivative with respect to K is 100 lambda. Okay, all right. And sure enough, the derivative with respect to lambda itself is just your condition. 50L plus 100K minus 8,000 should equal to 0. Of course, they all should equal to 0. Okay, all right. So this might look like an ugly function, but it's really not that bad. So what do we want to do again? We want to take the top two equations and get lambda by itself. So I will move it under here to give myself some room. So first of all, 200 times 3/4, 3/4 of 200 is 150. L to the negative 1/4, I will right away throw it on the bottom. I'm not going to waste time with that. And then the K to the 1/4 stays at the top. Okay, so I simplify this. Multiply these numbers. The L goes to the bottom. The K stays at the top. Equals to 50 lambda. Right? And again, how? Because we set it equal to 0, we'll move this over. Good. One more thing to do to get to lambda is to divide by 50. So lambda, if I divide both sides by 50, or multiply by 1 over 50 if you want. So lambda is 3, K to the 1/4 over L to the 1/4. Okay, not that bad. Now let's take the LK and do the same thing. Ooh, I forgot something. Oh yeah, I have it here. No, I didn't. It's behind. So 200 times 1/4, that's 50. L to the 3/4 over, this K has a negative 3/4, so I'll throw it on the bottom. Yes. So one more time, 200 times 1/4, that gives me the 50. Yes. The L to the 3/4 stays at the top, and this K to the negative 3/4 moved at the bottom. And that's going to equal to what? 100 lambda. Okay. So one more thing. Take and divide both sides. I can write this. Divide by 50. Yes, both sides. And that's how we came up with that. Now I'm going to divide by 100, both sides. So what do we get? We get that lambda is going to equal to the 50 and 100 reduce to a 1/2. Or it simply leaves me with that 2 on the bottom. Cool. That's actually pretty neat. So what we're going to do is, as always, set the two lambda equal to each other. So what I get is that 3 K to the 1/4 over L to the 1/4 is going to equal to L to the 3/4 over 2K to the 3/4, which is really nice. Why? How do I solve an ugly equation like this? Nothing easier. It's a proportion, right? We're going to cross multiply. And the good thing is that those exponents always supposed to add up to 1, because look what happens. 3 times 2 is 6. K to the 1/4 times K to the 3/4. What do I do with these exponents? Add them together. So 1/4 plus 3/4, that's 1. And then on the other side, L to the 1/4 times L to the 3/4, same thing, just gives me an L. And look how pretty this equation came up to be. And we're done, right, with that part. So even though it started pretty ugly, once you cross multiply, those exponents should always add up to 1. It's a fact. So it should give you always some nice equation like this. Good. What else do I have to do? I have to combine this equation that I got from the top two, right, derivatives, and combine it with the one on the bottom. Basically, I'm combining it with what? Our constraint equation, our condition, which in this case is the budget equation. There you only have $8,000 to spend, right, for labor and capital. Okay, so same thing as we did with the others. What are we going to do? Substitute, yes. So in place of L, I'm going to write 6K. So I have 50 times 6K plus 100K is equal to 8,000. So that's 300 plus 100, fine. So that's 400 divided out of 8,000 divided by 400. So this should be a 20. Yeah. So K is 20. Then L is what? 6 times 20, which is 120. So there you go. The maximum production will be reached in other words, maximum amount of units will be you can produce will be reached if you can use what? 120 units of labor, so hours of work paid to your employees, and 20 units of capital. And again, 1 unit of capital for your company could be $1 million invested, right? Or it could be $1,000 invested, or whatever your unit of capital is. It doesn't have to be $1. Again, you cannot be investing $20 into a company. That's not much of it. Okay, so what is that production? So remember, our Cobb-Douglas function, if I take back that paper, was 200 L to the 3/4 K to the 1/4. So put that in your calculator. I hope I have a number for that. I hope I have a number for that. I hope I have a number for that. Where is my number for that? I don't have a number for that. Please tell me I have one. Yeah, and I'm sure you're busily plugging the numbers in for me, so I don't have to worry about it, right? Is that what you're doing? Oh, there you go. 15. I'm getting 15335.63. So again, about what? These are units, right? These are not dollars. These are dollars, right? So units of labors times, right? $80 an hour, whatever that was. So 15,336 units produced. Okay, all right. Now, maximum amount of units under this budget constraint. That looks pretty good. Okay, so there's one last part to this, and I want you to find lambda and give me an interpretation for it. So I'm going to go back. Where is lambda? Lambda up here, I'm just going to take this aside. Lambda up here was 3 times K, which what was K? What, 20 to the 1/4 over L, which is 120 to the 1/4. So put that in your calculator. And what can we get? So that should be 96. Okay. All right. I guess that's what I have. If it's wrong, no problem. Let me know. So that's about 96, right? So that simply means what? For every extra $1 in the budget. So in other words, what? Past the 8,000, right, that we already have for the budget. So for every extra $1 that you can spend in the budget, you can make how many more? 96 more units. That sounds good. Okay, so at some point, just put in a little bit more cost, and then looks like you're getting a whole lot more out of it. So again, I hope this is correct. That's what I had. But yeah, I hope this is right. Okay, so put in your calculator, double check on me. But here it is.